In this lesson, we'll look at graphs of radical functions. First, let's look at the graph of the basic square root function and then cube root function. We're also asked to state the domain and range of each function. So, to graph this function, let's help ourselves with a table of values. That will be our input x and the output root of x. Okay, what kind of x values we can take and evaluate the root of it? Well, they can't be negative, so the lowest such number is 0. We need to remember that the radicand of any even degree root must be bigger equal 0. That's really our condition for the domain. Okay, so we already know the domain. Let's fill it in. The interval from 0 to infinity. That's our domain. So let's pick some higher numbers than 0. For example, 1 and 4. Numbers that are easy to evaluate root of. Root of 0 is 0, root of 1 is 1, and root of 4 is 2. We're ready to plot them. 0, 0, 1, 1, it's here. Let's mark the scale. And 4, 2. That's the point. And now we are ready to connect. When you connect the points, make sure that you keep in mind the vertex, the starting point. That's the first point of the domain. Our graph can't pass this point to the other side, right? Okay, let's join. Here's the shape of our root function. Good idea to remember this shape. 0, 0, 1, 1, and 4, 2. Okay, now let's look at the range. Remember, we can read the range from the graph by projecting the graph onto the y-axis. So all the points on the y-axis, starting from 0 towards infinity, can be taken. Even this point, since the graph is rising, sooner or later this point will be covered as well. So everything from 0 to infinity, that's our range. Here we go. Let's see our second basic function, cubic root of x. Well, this time we don't have any restriction for the domain. Cubic root can be taken of any real number, so the domain is all real numbers. And to graph our g function, we may help ourselves with a little table of values, input x, output cubic root of x. So now we can take some negative numbers and some positive numbers. It's always a good idea to take 0 as well. For easy calculations, let's take perfect cube numbers like -8, -1, 0, 1, and 8. Cubic root of -8 is -2, of -1 is -1, cubic root of 0 is 0, and then 1 and 2. Let's plot those points. Since our grid is still -5, well, we need to estimate. That's -6, 7, -8 approximately here. And then -2. So that's the point that belongs to the graph at -2 on y-axis. And the next point, -1, -1, so it's here. And then 0, 0, 1, 1. And again, extend this grid, 6, 7, 8 approximately here, and the value is 2. Okay, now we need to connect those points. It seems to shape like a sideways snake. Let's see it. That's our graph. Cube root shape. Okay, what's the range of it? Again, if we project our graph onto the y-axis, everything will be covered because remember, this graph is rising. So no matter how high is the y value, sooner or later it will be attained. Maybe very far, but it will be reached for sure. So the range is all real numbers as well. And here's our scale, 1 and 1. Great. Let's keep in mind those two shapes, square root of x and cubic root. The domain and range of square root of x is from 0 to infinity. The domain and range of cubic root is all real numbers. Now let's see how the graphs of those modifications of a square root and cubic root functions look like. Again, before we start filling up this table of values, it's a good idea to think about domain because we need to know what kind of x values we can take. To find the domain, we need to protect the radicand. The radicand, which is x minus 1, must be bigger equal 0. So when we solve this inequality, x must be bigger equal 1, and we already know the domain. The domain starts from 1 and goes towards infinity. Okay, so now we know what kind of numbers to take. We start from 1, the next one will be 1 higher, so it's 2, and 4 higher, so it's 5. This way it will be easy to calculate. If we choose less friendly x values, we'll have to approximate the corresponding y values, but that's okay too. We can round the y values to 1 decimal place and plot the approximate points. Okay, if we plug in 1 for x, so under the root we really have 0, so root 0 is 0. Plug in 2 for x, 2 minus 1 is 1, root of 1 is 1. Plug in 5 for x, 5 minus 1 is 4, root of 4 is 2. Keeping in mind the shape of the basic root function, we may predict that the shape of this function will be similar. Maybe moved somewhere, but very similar. So those 3 points should give us enough information to graph. Okay, let's plot them. 1, 0, that's this point. It belongs to the graph and it is on the x-axis. 2, 1, 2, 1 is here. Okay, and 5, 2, 5, 2 is over there. Since 1, 0, that was our vertex, we need to start graphing from this point to the right. The graph will never pass that point, so that's important. That's our vertex, right? Okay, let's join those points. Here is our graph. If we project this graph onto the y-axis, all points starting from 0 towards the infinity will be covered by this projection. So the range of this function is from 0 to infinity. Now let's notice the relation of the graph of our f function to the graph of the basic square root function, which goes somehow like this. Well, it looks like this curve is moved 1 step to the right. So the transformation of the basic shape is the translation by 1 step to the right. In shorter notation, we can say capital T for translation and just give the vector by which we are translating the basic shape. That means move 1 horizontally, first coordinate 1, and no vertical movement, so second coordinate 0. Vector 1, 0. Okay, let's see the second function. Again, we are going to use table of values x and then negative cubic root of x plus 2. What kind of x values can we take? Actually anything, because we can take cubic root of any real number. So the domain of this function is all real numbers, not a problem here. Okay, let's take some negative numbers, some positive numbers, and 0 as well. To make our calculations easier, we are taking perfect cube numbers. So negative 8, negative 1, 0, 1, and 8 should be good enough. Okay, so what do we have here? Negative cubic root of negative 8 is the same as negative 2, and then plus 2. So we have plus 2 and plus another 2, it's 4 altogether, right? Next, negative cubic root of negative 1 is negative 1 plus 2. So we have plus 1 plus 2, it's 3. 0 plus 2 is just 2, that was easy. Negative and then cubic root of 1 is just 1 plus 2, so the answer is 1. And negative cubic root of 8 is 2 plus 2, so we end up with 0 here. Okay, we are ready to plot. This will be the g of x function. Negative 8, that will be negative 6, 7 approximately here, result in a value of 4. So it's somewhere here. Negative 1, 3, 0, 2, that's this point, 1, 1, and 8, 6, 7, 8, somewhere here, 0. So that will be this point. Okay, it looks like the points seem to line up in a horizontal snake shape. Let's join them. Here's our sideways snake. Again, if we start projecting our graph onto the y-axis, everything will be covered. Sooner or later, all values will be taken. So the range is also all real numbers. What about transformation of the basic cubic root shape? Well, let's recall that basic cubic root shape looks like this, right? So how did we obtain the purple graph out of the red graph? Well, since the purple shape decreases and the red shape increases, let's first flip the red shape over the x-axis, so the new shape looks somehow like this blue one. And then if we move the blue shape 2 steps up, it will match exactly the purple graph. It's enough to watch the central point of the shape. It was moved 2 steps up to the new position, isn't it? Okay, so we can say the first transformation was the flip over x-axis, and the second transformation was the translation by 2 steps up. This flip over the x-axis we could record more formally as symmetry in x-axis. And then the 2 steps up, that's our translation by the vector horizontally 0 steps and vertically 2 steps. So translation by the vector 0, 2. Here we go.